Okay, let's go back to example number 6. Okay. Looking at this integral, what would be a good first step?
Separate bottom. Separate bottom.
Separate the bottom, factor the factor at the bottom. All right, but before doing the factoring, there's something else that we need to check for each polynomial in the numerator and the denominator.
Long division.
Long division first, right? And that's because the degree in the numerator is larger than that in the denominator. All right, now notice something else. So we have an x cubed. We're missing the square term, which is fine. Well, we can write it down, and we will write it down when it comes, because when it comes to doing the polynomial long division, it's going to be a lot helpful, so we can organize everything power by power. So let's set up the polynomial long division. That'll be x cubed plus 0x squared plus x minus 3 and divided by x squared plus 0x minus 4. And well, to do polynomial long division, recall we divide the leading term of the dividend by the leading term on the divisor. So x cubed over x squared, that's going to be x. Let's write it down on top of the power x's. So in this case, that will be x times x squared, that's going to be x cubed. X times 0x, that's a 0x squared. And x times negative 4, that's negative 4x. But recall that we always change the sign of what we get, because technically we're subtracting. And by subtracting, that changes the sign. So then this is 0 minus, and that becomes a plus. So here, notice how the cubes cancel. And okay, let's drop the next one. So that's simply 0x squared, and that's a 5x minus 3. But in this case, we don't need to write that x squared. And in this case, we're done with the division, and that's because the new polynomial that we obtained here, it's not the same degree, and it's actually lower in degree than that in the divisor. And we continue with more iterations of the division whenever this first remainder is still the same degree or higher than the one in the divisor. So in this case, we're done. So let's write this in the format quotient plus remainder over divisor. That's equal to the integral of x plus remainder 5x minus 3 over x squared minus 4. All right. Well, in this case, what can we do? And by the way, what did I do on my notes? I think I did something weird. Oh, never mind. Okay, so number one, we need to split the derivative. Well, we need to, so that's not the derivative, the integrals into x dx plus the integral of 5x minus 3 over, how about instead of x squared minus 4, let's write it x plus 2 and x minus 2. Let me do the x minus 2 first. And it is the second integral, the one that requires partial fraction decomposition. So let's go ahead and take care of the partial fraction decomposition right below. Alright, so I'm going to skip the first integral for a while, and let me focus on the second integral. So I use a different color here. So the integral of 5x minus 3 over x minus 2, x plus 2. This is the same as saying, well, the integral of a over x minus 2 plus b over x plus 2. So let's do the partial fraction. Well, let's figure out a and b. Well, this one is going to be very short because they're all linear. None of them are repeated. So 5x minus 3 over x minus 2, x plus 2 So that's a over x minus 2. And let's multiply by the least common denominator, which in this case is x minus 2 times x plus 2. X minus 2 times x plus 2. And simplifying this should give us 5x minus 3 because everything cancels. And notice when we distribute over the second term, over the right hand side rather, the x minus 2's cancel on the first term, leaving us with a times x plus 2. When we do the second distribution, the x plus 2's cancel and we are left with b times x minus 2. And that's our basic equation. Alright, so let's choose convenient values, and in this case it's not going to be like the previous examples that we did. These numbers are really going to be nice. So how about x equals negative 2? And also x equals to 2. Those are going to work really nicely. And well, let's write this down. That's 5 times negative 2 minus 3 equals a times negative 2 plus 2 plus b times negative 2 minus 2. That's a negative 2, and negative 2. Of course, this term is going to go to 0 because negative 2 plus 2, that's a 0. And be careful with the negative signs here. That's 5 times negative 2, which is negative 10, minus 3. That's going to be negative 13. Equals negative 2 minus 2. Also be careful with the negative signs. We add the two numbers. That's a negative 4a. And a equals 13/4. Alright. Let's do the x minus, or the x plus 2. Yes. Yeah, it was supposed to be b. Yep. And for x equal to 2, so we're going to have 5 times 2 minus 3 equals a times 2 plus 2 plus b times 2 minus 2. So 2, 2, and 2. And of course that last term will get cancelled because 2 minus 2 is 0, 0 times b is 0, that whole term goes to 0. 5 times 2, which is 10. 10 minus 3 is 7. 2 plus 2 equals 4a, and a equals 7/4. Alright. And we may go back to the original integral. We just found these two values of a and b. Okay, so we splitted this integral into the integral of x dx plus, what was a? A was supposed to be 7/4. And b, which is 13/4. And well, these three integrals, general power rule for the first one, x squared over 2, and plus 7/4 ln absolute value of x minus 2, 13/4 ln of x plus 2 plus c. Final answer. Alright. Questions about this example? Alright, let's have a look at the last example and let's get prepared. This one is going to take a really good minute to go through. Alright, so what do we have? The integral of x cubed plus x squared, whole thing over x squared plus 4 quantity squared. So number one, what about that x squared plus 4? Is that linear repeated because of the power 2? Or is that something different? If so, what is it? What is that? Huh? We can't.
What's it called? I lost it somehow.
It's well, we have an exponent 2. What does that exponent 2 tell us? Quadratic. Is that reducible or irreducible? Irreducible. So we need to do the ax plus b over x squared plus 4. But in this case, it's also repeated. So we need to write down another term. Cx plus d x squared plus 4 quantity squared dx. All right. Okay, so let's see. Let's set these two quantities together. This one right here equal to that whole splitted fraction. So x cubed plus x squared divided by x squared plus 4 squared equals to ax plus b over x squared plus 4 plus cx plus d x squared plus 4 squared. So the usual, we need to multiply both sides by the least common denominator to simplify the equation, so we can work with something a lot more simple. So, and that least common denominator, well, we need to cancel x squared plus 4, but we need a powerful enough to cancel x squared plus 4 to the second power. So in this case, x squared plus 4 to the second power. And that's going to do it here. So when we distribute on the left hand side, everything cancels except the numerator. That's x cubed plus x squared equals, okay, so in the numerator we're going to multiply on the right hand side. Notice how only one power because technically this is an x squared plus 4 to the first power. One power of x squared plus 4 remains that multiplies with the ax plus b. And distributing on over the second term, both powers of x squared plus 4 get cancelled, leaving us with cx plus d. And this is our basic equation. The equation that we will use to find a, b, c, and d. Okay, so let's see. Any convenient values that zero some stuff out and we can figure out a letter A or B or C or D. Well, on the one hand, we have a problem here. We could have zeroed out this ax plus b if we had some number over here that gets to 0, but unfortunately there's no way, because that's x to the 4, that's x squared plus 4 is never 0. Alright? We cannot plug in x equals to negative 4 because negative 2, because negative 2 squared is also positive 4 plus 4. Well, that's not going to kill this term right here. Maybe if x equals to 0, we can only cancel c. Alright? But we will still be left with a bunch of numbers. We would be left with b and we would be left with d. Okay, let me write it down. For x equals 0, this one goes to 0 and that one also goes to 0. That one also goes to 0, 0, and well, let's see, we would be left with 0 here as well. 0, we would be left with B and D. We would be left with one equation and still two unknowns, right? So there's nothing else. Well, using the convenient value strategy is not going to work. Okay, so we're going to do something else. We're going to do what we call the undetermined coefficients. Yes?
I was like, can you distribute x squared plus 4 to ax plus b, and you get ax squared plus 4 plus bx squared plus 4?
Mm-hmm.
You can cancel out the a that way, you get the b, c, and d.
Yeah, so we're going to distribute, and then we're going to equate coefficients in a different way. And the reason why I'm going to do this is because this is like, I don't know, like one of the basic principles to when you go to differential equations. Actually, there's one section in that class in which you will do this equating coefficients, and not just with x's, but also exponentials, trigonometrics. It's gonna get pretty fun. Actually, one problem typically takes like 3 or 4 pages to solve because of the size of the method of the problem. So let's do one of those. So let me do x cubed plus x squared equals, okay, ax times x squared, ax cubed, ax times 4, 4ax, b times x squared, that's bx squared, and b times 4, 4b, plus cx plus d. All right. Now, what are we going to do from here? What we're going to do is group everything in terms of the corresponding power. So, what do I mean by that? X cubed plus x squared equals to, okay, I'm going to leave. Okay, let's look at this ax cubed. Do we have another cube term? No, that's the only one, ax cubed. Okay, what about the quadratic terms? How many do we have? Do we have another one besides b? I don't think so, right? What about linear terms? That is, terms that contain x to the first power. Okay, let me highlight them. Okay, we have one here, and we have another one here. So that's going to be 4a plus c times x. All right? And last but not least, we have the constant term, the group of constant terms, which I will highlight with this color. And let me just put them together. That's all I'm going to do here. So plus parentheses 4b plus d. Now, how does the equating coefficient or undetermined coefficient method works? Well, okay, let me make this a little more simple. So what if I have something like 3x squared equal 3x squared plus 4x plus 3 equals, okay, these two polynomials are the same because the powers are the same and also the coefficients are the same. I know I'm just writing a polynomial equal another polynomial. What's impressive about that? Well, so the thing I'm saying is I'm relating the coefficient of x squared with the coefficient of x squared. It's the same. It's the same. It's the same, right? And in this case, well, let's take this idea to this problem here. Well, we need to compare the coefficient of x cubed. We need to compare the coefficient of x squared. We need to compare the coefficient of x to the first power, and we need to compare the coefficient of basically x to the 0 power. But in this case, we're missing some terms. We wish we had the x to the first power and the constant term. Of course, we can make our wish come true by just adding placeholding zeros there. X cubed plus x squared plus 0x plus 0. What's the coefficient of x cubed here? Right here. 1. Let's write it down. Why not? What's the coefficient of x squared? Also 1, right? This means that a equals to 1. Let's write down a system of equations actually. Yes, I know that when I say let's write a system of equations for unknowns, sounds scary, but you'll see. A equals to 1. From the second equating of coefficients, what is b equal to? Also 1. And well, for the coefficient of x, what is 4a plus c equal to? 0. And last but not least, what is 4b plus d equal to? 0. Okay, the good thing, yes, we have 4 equations, potentially 4 unknowns, but we don't really have 4 unknowns. We already know 2 of them, right? We know the value of a, we know the value of b. Okay, let's use them. Plug it in the third equation to find c, and plug in b equals 1 on the fourth equation to find the value of d. And that's how we're going to go about this one. So 4 times a, which is 1 plus c, equals 0. So that's c plus 4 equals 0, and c equals negative 4. And for the second equation, 4b, which is equals to 1, plus d equals to 0, d plus 4, and again, d equals negative 4. All right? So we just found the coefficients or the letters a, the values of the letters a, b, c, and d that split the partial fractions so we can integrate. All right. Let's see. Okay, let's go back to the integral. So a, which is 1x plus b, which is also 1, over x squared plus 4 dx plus the integral of c, which in this case it was at negative 4? Yeah. Negative 4x minus 4 x squared plus 4 squared dx. So we need to compute that integral. All right. So we will split these two integrals into a total of 4 integrals. And I like this example because on this example we will pretty much use every single method of integration that we have covered during, well, I believe we start working last week and this week as well. You'll see how this works. So let me split this integral the following way. That's the integral of x over x squared plus 4 plus the integral of simply 1 plus, actually I'm going to write that as a negative 4 minus 4 times the integral of x squared plus 4 squared dx minus 4 times the integral of dx over x squared plus 4 squared. 4 integrals that we're going to have a look at. Let me label them. Let's label them 1, 2, 3, and 4. And let's work on them individually. Okay, the first one. Let's have a look at the first one. Okay, number 1. That's the integral of x over x squared plus 4 with respect to x. Well, in this case, any ideas on what method to use? Use of, because the derivative of x squared plus 4, which is 2x, we have that power of x multiplying the dx, which is great. Let's go ahead and do that. Okay, so u equals x squared plus 4, du equals 2x dx, and x dx equals 1/2 du. Writing the integral, we get the integral of 1/2 du over u. That's 1/2 the integral of du over u, which is 1/2 ln of u. Well, potentially absolute value of u. But in this case, when we back substitute this 1/2 ln of x squared plus 4, we really don't need those absolute value bars, because this x squared plus 4 is always positive, so we're not in danger here. So that's the first integral. All right. The second integral, number 2. And let me write that down. That's the integral of dx over x squared plus 4. Any ideas on this integral? Arctan rule? Sounds good, because in this case we don't have that power of x multiplying the dx, which tends the du part of the problem if we chose to use the u substitution method. In this case, well, the integral of something squared plus something squared, that's x and 2. And then recall that the integral for arctan, that's 1 over a, 1 over 2 arctan of u. So technically, okay, let me write it down. So this means u equals x du equals dx. Yes, great. We don't need to compensate any values. That's that's a equals to 2, which is this value right there. And from here, well, u, which is x over 2. And well, I shouldn't write the plus c. We're fine without the plus c. We're gonna write those plus c's at the end. All right. The third integral. Let's have a look at the third integral. So I think I'm gonna use the back side of the page, the next page. Okay. Are you missing anything before moving on? Do you still need to work on anything? Okay. So number 3. So that's the integral x dx over x squared plus 4 quantity squared. All right. Any ideas on integral 3? Someone else besides Adrienne? Yusuf? Why not? Because u equals x squared, the derivative is 2x. We have, and it's very similar to the first integral, except for we have a power 2, but doesn't matter. That's going to be 1 over u squared. So let's go ahead and set it up. U equals to, let's see, x squared plus 4 du equals to x dx, x dx equals to 1/2 du. That means the integral of 1/2 the u over u squared. Let me take the 1/2 outside of the integral, and let's write this u squared that it's in the denominator towards the numerator so we can integrate. Recall, we cannot integrate variables while they're in the denominator. And while using the general power rule, this is 1/2 times u to the -1 divided by -1. But let's simplify this. Let's clear those negatives. Let's clear those signs. So that's going to be -1 over 2 times u, which in this case is -2 times u, which is x squared plus 4. So that's the third integral. Yes?
Isn't it multiplied by 4?
By 4. I'm going to do that at the end.
Oh.
Yeah. Yeah, I'm going to do that at the end. I'm just taking the integrals individually, so we don't have to deal with all these coefficients. But yeah, that's true. Integral number 4. Okay, the integral of... Wait. The integral x squared plus 4 quantity squared dx. Any ideas on this one? This one is a fun one, by the way.
You can use trig substitution if you modify.
We can use trig substitution, yes. Well, number 1, we cannot use the regular u substitution because we don't have that factor of x, like in the previous example. We cannot use the arc10 rule at the same time because we have this power of 2. We can use trigonometric substitution, but I mean, we were under the impression that trig substitution works when you have this radical integrand, but this is not a radical integrand, but we can turn this into a radical integrand if we use the following trick. Well, it's really not a trick, it's algebra. Isn't it x squared plus 4 to the second power the same as saying to the 4 over 2? Because 4 over 2 equals 2. And recall from properties of radicals that the index of the radical comes from the denominator of the rational exponent. And surprise, we have a radical. The whole thing to the 4th power. All right. Okay, so let's have a look at this integral. Let's apply what we learned last time in trigonometric substitution. Okay, so our focus is the quantity inside of the radical. Number 1, do we have a difference of squares or do we have a sum of squares? We have a sum of squares, all right? That means, okay, this is the angle theta, and let's set this as our u equals to x and a equals to 2. So when we label this, that's I mean, again, you can label your triangle. Well, in this case, these two quantities x and a will represent the sides of the triangle, not the hypotenuse. All right. So, and in this case, you can put them in the order that you want. In the end, you will get similar answers, equivalent answers in terms of different trigonometric functions. But again, my advice is to have your variable facing the angle, that is being the opposite side, and the constant term to be the adjacent. And of course, if we do the Pythagorean theorem, 2 squared plus x squared, that's going to give us x squared plus 4. Take the square root to get the length of the hypotenuse. That's the square root of x squared plus 4. And I think we're ready to set up a problem right here, number 1. So here is where we decide which one is the easiest of the two. Is radical over 2 or radical over x the simpler one? Which one is it? Radical over 2. And what trigonometric function does that relate? Secant. And I'll just secant. And solving for the radical, because we need to solve for the radical. Okay, so score for the first part of the trig substitution. Alright, so we need now another piece of information so we can get an x, so we can obtain a dx, so we can do a differential from the world of x to obtain a differential in the world of the angles, in the world of theta. So in this case, what we do is relate x and write either x over 2 or x over the square root of x plus 4. But which of those two is simpler? X over 2. And which trigonometric function is that? Tangent, because that's opposite over adjacent. And x equals to 2 tangent. And from here we're ready to take that du. So, or rather dx, not du. dx, the derivative of tangent, which is secant squared, and we have everything that we need. Let's go back to the integral and replace square root of x plus 4 with 2 secant, but be careful, because this 2 secant is raised to the 4th power. And in the denominator we will replace the x with the corresponding dx in the world of theta, that is 2 secant squared theta d theta. Alright? So far so good up to this point? Okay, so let's see. Number 1. Okay, let me take these 2 out of the integral. And that's a secant squared for now. And 2 to the 4th power, isn't that a 16? And we have secant to the 4th power. And in this case, well, we can simplify this integral. 2 over 16, that's a 1/8 secant squared in the denominator. Alright? We wish we had that secant squared in the numerator. That way we could have gone directly to tangent, because the integral of secant squared is tangent. However, that's not the case, but we have other ways to keep moving. Okay, well, I mean, if u equals secant, the derivative is secant tangent. No, we don't have that in our integrand. We can use another trigonometric identity. We can move the secant squared to the numerator in terms of which function? Cosine. So that's cosine squared theta d theta. Alright? Okay, so let's see. If u equals cosine, du will be negative sine. No, we don't have that factor of sine multiplying the d theta, so we can have that expression that stands the du part of the substitution. So we need something else in this case. Notice we have an even power. That's going to take us back to section 8.3, trigonometric integration. So what do we do? Which identity? Yes, an identity, but which one? I'm going to give you a hint. It's a half angle identity, which we usually call the power reduction formula, right? And I'm writing it in a different way just to save time. I'll show you. Technically this is 1 plus cosine over 2, but I'd rather have it multiplying by 1/2. Dividing by 2 is the same as multiplying by 1/2, so I can immediately multiply this by 1/8 to obtain 1/16 integral 1 plus cosine 2 theta d theta. And let's split into 2 more integrals. That's 1 over the integral, or 1 over 16 the integral of d theta, plus 1 over 16 the integral of cosine to theta d theta. And well, the first one is really easy to compute. That's just 1/16 theta. And from here, the integral of cosine is sine, but that's 1/16 times 1/2 sine 2 theta plus c. And simplifying this is 1 over 16 theta plus 1 over 32 sine 2 theta. Oh, I was not supposed to write the plus. We're gonna write it down at the very end. Okay, so we're done with the problem in the world of theta. We need to bring this back to the world of x. So we need to substitute back this theta. And we get this done by solving for theta over here from there. That's theta equals arctan of x over 2. And on the other hand, well, notice this sine of 2 theta. Recall that the trigonometric substitution for which we use this triangle right here, it's only good for theta, not for 2 theta. That means that we need to use another trigonometric identity. So that's 1 over 16 theta plus 1 over 32 times sine of 2 theta. What is that? Isn't it from our trigonometric identities?
2 sine cosine.
2 sine cosine. And this reduce. And well, theta equals arctan of x over 2 plus 1 over 16. Okay, sine from the right triangle, sine which is opposite over hypotenuse, that is x over the radical, times cosine which is adjacent over hypotenuse, that is 2 over the square root of x squared plus 4. And well, of course, let's simplify this before we go back again to the very original problem. Okay, the first term is fine. 1 over 16 arctan x over 2. And well, this is 2x, but these 2 reduces with 16 to give us a 1/8. And what happens when we multiply 2 radicals containing the same quantity inside? So we're multiplying it by itself. It's getting squared. That square cancels the radical, leaving us with simply x squared plus 4. Alright? That's because this is basically x squared plus 4 to the 1/2, right? Times itself. And because we're multiplying the same quantity, what we do is to add the exponents. What is 1/2 plus 1/2? Isn't that this invisible one right here? Yep. So that's another way to visualize. The other way is to multiply these two together, x squared plus 4, because we multiply them together and cancel the radical with the square, which is what I mentioned before. Alright, so to write this in a little nicer way, just like this. Alright, and we're done with integral number 4. So now we're ready to backtrack and go back to the original problem. Okay, so integral number 1. Okay, let me just go back to the previous page where we set up the integrals right here. So that's integral 1 plus integral 2 plus integral 3, minus integral 4 times the integral 3 minus 4 times the integral 4. Okay, so the first integral, according with my notes, okay, what we got for that one? Back to original. So that's 1/2 ln of x squared plus 4, alright? Plus the result of the second integral, that is 1/2. Did we get arctangent? And then here is where we include our coefficients. In this case, it was a minus 4 times the result of the third integral, and that result of the third integral in this case, it was where's my values here, times 2x squared plus 4. Alright, And for the last term, minus 4 times whatever we got from doing this trigonometric substitution, which in this case is 1 over 16 arctan x over 2 plus x over 8 x squared plus 4. Alright, so that's our final answer, Nick.
Wasn't the third integral the answer negative?
Yes.
So we have to do negative 4 times.
Yes, and that's going to cancel that negative later. So let's keep simplifying this, because notice we have some like terms. I believe just, okay, the first one, that's fine. That's 1/2 ln x squared plus 4. Okay, so we're going to have a plus a half arctan x over 2. And the negative times the negative is positive. 4 over 2, isn't that a 2? Over x squared plus 4. Alright. And 4 over 16, isn't that a 1/4? Arctan x over 2. And negative 4, that also distributes with this. Okay, 4 over 8, isn't that negative a half? Negative, okay, let me do negative x over 2 x squared plus 4. Alright, so let's combine like terms, and we can add the plus c actually here. Okay, to combine like terms, we have a couple of them. Number one, I'm going to combine these arctan terms, and I'm going to combine these terms right here. Alright, so on the one hand, I need an LCD. I'm missing some factors. I'm going to multiply this by 2, divide by 2. Alright, oh wait, no, you know what, never mind, because this one has an x, this one doesn't have an x, so no worries, I'll take that back. These are not like terms, only the yellow ones. Alright, so what's 1/2 minus 1/4?
They wouldn't, don't they? Wouldn't it be 4 minus x?
4 minus x, oh yes, we can do it, why not? That's true, because we will end up with the same denominator, and that's a 4 minus x, right? Then we can put them together more compact. Sure, that works. That's 1/2 ln x squared plus 4, and a half minus a fourth, isn't that a fourth? And well, combining these other two, that's 4 minus x over x squared plus 4. Alright, plus c. And is there anything else? Yes.
We got the 2 times x squared plus 4.
Yeah, the 2, right? And we're not done. We just need to box the final answer. All right. And